Hello students, welcome back to lecture number 16, the basics in fluid mechanics. Actually today is the last lecture of chapter number 1, in which we are going to discuss about numericals on pressure measuring devices. Already in last lecture we have seen some numericals based on pressure measuring devices, in which we have discussed about pressure measurement by using single tube manometer, that is piezometer, single tube manometer, and etc. And on that we have solved some numericals also. In today's lecture we are going to see few more numericals, and we are going to stop at here with the chapter number 1. After end of this chapter I will give you one quiz, that is MCQ test, online test. You please attempt all of those. This will be considered as your assignment, as well as I will share you one question bank to you, on which some problems are given. You have to solve those problems and share it to me with the help of PDF. You should convert it in a PDF and share it to me on my mobile number or on my WhatsApp number. Okay. So we'll start with the single column manometer. So already we have seen the theory behind the single column manometer. This is the example of single column manometer, where we wanted to measure the pressure. Let H1 be the height of reservoir to the point A1 whose pressure we wanted to measure. Delta H with change in reservoir with respect to its datum position due to additional pressure in a container A. And that change in height is causes here rise in capillary tube up to level H2. Rise in capillary level up to or tube level up to H2. So we know that fall of heavy liquid in reservoir will cause a rise of heavy liquid in the right limb. So A into delta H is nothing but, here capital A into delta H is nothing but small a into H2, and therefore delta H can be given as A plus A into H2 divided by capital A. What is A? Capital A. Capital A is nothing but the cross-sectional area of reservoir. Small a is nothing but the cross-sectional area of tube. So from that we have calculated as P2, sorry, root 2 into G into delta H plus H2 is equals to rho 1 into G into delta H plus H1 plus PA. PA is nothing but the pressure inside the reservoir A. Now consider this is a single column manometer used to a pipe containing a liquid of specific gravity 0.9 as shown in figure. Find the pressure in pipe if the area of reservoir is 100 times the area of tube from the manometer reading as shown in figure. The specific gravity of mercury, we all know it is 13.6. So this is the figure. The fluid which is filled inside the container having specific gravity of 0.9. So can you tell me its density? Its density is 900, because specific gravity is nothing but density of fluid divided by density of water, and density of water is 1000, and that's why density of fluid inside the container A is equals to 0.9 into 1000 is nothing but 900. H2 be the height of reservoir. Delta H with the change in reservoir height. Sorry, H1 is the height of reservoir. Delta H with the change in height. And H2 is nothing but the rise in water level, mercury level inside the single column manometer, and it is equals to 40 centimeter. Okay, and the specific gravity of manometer is 13.6. So its density is 13.6 into 10 to power 3 or 13,600 kg per meter cube. So we have calculated rho m is equals to 0.9 into 10 to power 3. Rho m is equals to 13.6 into 10 to power 3 kg per meter cube. One more thing is given here is the find the pressure in pipe if the area of the reservoir is 100 times the area of tube. So capital A by small a is nothing but 100. H1 is equals to 20 centimeter, it is nothing but 0.2 meter, and H2 is equals to 40 centimeter, it is nothing but 0.4 meter. Okay, so from this given we have to calculate PA, pressure at point A. So we know that delta H is nothing but rise of fall of or change in height of reservoir, and it is given as small a by capital A into H2. So because delta H into A is nothing but small a into H2. So delta H can be given as 1 by 100 into 0.04. So delta H can be given as 0.004 meter. Delta H is nothing but 0.004 meter. Now in equilibrium condition, from figure we know that pressure in left limb is equal to pressure in right limb. So PA into rho A into G H1 plus delta H is equals to PM into G H2 plus delta H. So put out the values, we'll get PA value is equals to 51.89 into 10 to the power 3 Newton per meter. 51.89 into 10 to the power 3 Newton meter. Similarly, similar kind of problem we can solve with the help of inclined column manometer. So this is the example of inclined column manometer, where the rise in capillary level is L, which is measured with the vertical height H2. H1 be the height of point where reservoir A from the reservoir tank. Delta H be the rise or fall of fluid level inside the reservoir. Theta be the angle of inclination. So we know that H2 is equals to vertical rise of heavy liquid in right limb column is equals to L sin theta, and therefore H2 is equals to L sin theta. From equation, from equilibrium equation, pressure at A is given as PA is equals to H2 G2 rho 2 G minus H1 rho 1 G. So putting the value of H2, we can get PA is equals to sin of theta into rho 2 G minus H1 rho 1 G. L sin of theta, sorry, not only sin of theta, here by mistake I have written sin theta. In inverted U-tube differential manometer, again we are going to, if it is of same height level, we will equate the two pressures PA into rho 1 G1 H1 is equals to PB into rho 2 G2 H2. PA minus rho 1 G1 H1 is equals to PB minus rho 2 G2 H2 minus rho S GH. Okay, so we'll solve some problems with respect to this. In figure, an inverted differential manometer is connected to 2 points A and B, which convey a water. The fluid in a manometer is oil of specific gravity 0.8. From the manometer reading shown in figure, find the pressure difference between A and B. Now here, see, the difference is that instead of using mercury as a measuring fluid, we have used oil at here in inverted U-tube manometer. That is the first thing, of specific gravity 0.8, and that's why you can say that its total density is 800 kg per meter cube. Now level of, another thing is that level of A and B is not same. The reservoir A is 20 mm above the reservoir B, 20 mm above the reservoir B, but with respect to reference line, the manometer height is 30 cm for reservoir A and 30 cm for reservoir B. So from this given data, we have to solve the problem. So difference in oil level in two limbs is equals to 30 plus 20 minus 30 is equals to 20 cm. So we have got idea that from reservoir A to this height is 30 cm, and from here to this height is 30 cm. So how to calculate difference? We know that total height is 50 cm minus change is 30 cm. So height of oil level is equals to, with respect to reference line in right limb, is equals to 20 cm. So this is H1 is equals to 0.3 meter. This is H2 is equals to 0.3 meter, and this is H3 is equals to 0.2 meter. Now with respect to datum line XX, pressure in the left limb below XX is given as PA minus rho 1 GH1. So it is equals to PA minus 2943. Okay. Pressure in right limb is equals to PB minus rho GH2 minus rho GH3. Ata here rho is nothing but here density of oil. So the change is PB minus 1000 into 9.81 into 0.3 minus 800 into 0.981 into 0.2. So it is PB minus 4512.6. Now equating two pressures, PA minus 2943 is equals to PB minus 4512.6. PB minus PA can be given as 1569.6 Newton per meter square. So by this we can say that the difference between pressure difference between limb A and B is 1569.6 Newton per meter square. Okay. This is one another problem in inverted U-tube manometer is connected to two horizontal pipes A and B through which water is flowing. The vertical distance between the axis of these pipes is 30 cm. When an oil of specific gravity 0.8 is used as a gauge fluid, the vertical height of water column in the two leads of the inverted manometer when measured from the respective center lines of the pipes are found to be same and equals to 35 cm. Then determine the difference of pressure between the pipes. Okay, so in this problem, reservoir A is filled with water, reservoir B is again filled with water. The change in height of oil of specific gravity 0.8 with respect to datum line CD is 30 cm. The difference between reservoir A and B is again 30 cm. The height of datum line to reservoir point A is 35 cm and reservoir B to the datum line is 35 plus 30 cm. It is similar kind of problem. The specific gravity is given, it is 0.8. So pressure at point C is equals to PA minus rho GH. So here H is nothing but, for left limb it is actually, for H is nothing but 35 cm. At pressure at point D is nothing but PB minus rho 1 GH1 minus rho 2 GH2. So it is equals to again same. But pressure at C is equals to pressure at D. That is again it is equating with 1 and 2. PA minus PB will be given as equals to 2354.4 Newton per meter square. It is similar kind of problem which we have solved previously. Now this is somewhat interesting problem. Here determine the pressure difference PA minus PB when the reading of manometer is as shown in figure. Okay. We want to simplify it initially. Then and then it can be possible to solve this problem. Now see here carefully. This is reservoir A, this is reservoir B. With respect to this datum line, reservoir A is 24 cm above, reservoir B is 10 cm above. Now this is filled with the fluid inside the reservoirs. This is downward water level of 12 cm. This is high up to 10 cm and here it is up to 15 cm. The fluid which is used here having specific gravity of 13.6, which is used at here having the specific gravity of 0.8. Now with respect to this datum line, pressure is same at both ends. Pressure is similar and same for the both ends. So taking equilibrium from datum XX for left part and dummy YY for right part, then PA into 0.24 into 0.8 into 10 to the power 3 into G is equals to 0.12 into 13.6 into 10 power 3 into G into P1, and now P1 is nothing but this pressure. P1 is nothing but this pressure. So PA1 is equals to PA plus 188 into 10 to power 3 minus 16 into 10 power 3. So P1 can be given as PA minus 14.12 into 10 to power 3. Have you understood? We have simplified this problem into two categories. This is one U-tube manometer. This is another U-tube manometer. Here the pressure applied is P1. Here the pressure applied is PA. So consider it here it is a dummy reservoir having pressure of PA. Now this is the simple problem. Here the height is only 12 cm with respect to datum line, and here height is of 20 cm. 24 cm, sorry. So from that we have calculated a PA. Now consider similarly like this, another reservoir. In this reservoir, P1 into 0.10, P1 into 0.10 into 0.8 into 10 to power 3 into G is equals to 15 into 13.6 into 10 to power 3 into G plus PB. So P1 can be given as P1 is equals to PB plus 20.01 into 10 to power 3. Now equating P1 and P1 both sides, we can say PA is equals to PA minus 14.12 into 10 to power 3 is equals to PB plus 20.01 into 10 to power minus 3. So PA minus PB can be given as 34.13 kilopascal. Now this is the problem. The water in a tank is pressurized by air, and the pressure is measured by a multi-fluid manometer as shown in figure. The tank is located on a mountain at an altitude of 1400 meter, where the atmospheric pressure is 85.6 kilopascal. Determine the air pressure in the tank if H1 is equal to 0.1, H2 is equal to 0.2, and H3 is equal to 0.35 meter. Take the density of water, oil and mercury to be 1850 and 13,600 kg per meter cube respectively. Okay, this is the problem where air and water contains the reservoir is there. Air having pressure P1 as located here. Then this water is raised at here. It is differentiated with the help of oil, and oil and mercury is differentiated with this U-tube manometer. So here H1 is equals to 0.1 meter, H2 is equals to 0.2 meter, and H3 is equals to 0.35 meter. It is given in the problem itself. Rho 1, that is rho of water, rho of oil, and rho of mercury is also given. Now starting from point 1 at air-water interface, here air-water interface, moving tube by adding or subtracting up to the point 2, P1 plus rho of water into GH1 plus rho of oil GH2 minus rho of mercury GH3 is equals to P atmosphere. Have you understood how we have considered? From this point to this point, we have taken the overall behavior of this pressure. P1 be the applied pressure at here. Atmospheric pressure is at here. Then how to measure the compare it? Because atmospheric pressure, the mercury level stopped at here, so it is counterbalanced by atmospheric pressure. So P atmospheric pressure is equals to the total of pressures at here. So P1 plus rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3. By that we have got P atmosphere. Solving for P1 and substituting the values, P1 is equals to P atmospheric minus rho water GH1 minus rho oil GH2 plus rho mercury GH3. So by solving it, we will get P1 is equals to 130 kilopascal. Similar kind of problem is here. The manometer is used to measure the pressure in the tank. The fluid used for the specific gravity of 0.85 and manometer column height is of 55 centimeter as shown in figure. If the local atmospheric pressure is 96 kilopascal, determine the absolute pressure in the tank. Again, we know that rho is equals to 850 kg per meter cube. So from figure we can write P is equals to P atmospheric plus rho GH, and by solving we will get 100.6 kilopascal. Pressure variation in at rest, that is hydrostatic law. What is hydrostatic law? The rate of increase of pressure in a vertically downward direction is equals to the weight of density of fluid at that particular point. So delta P by delta Z is equals to rho into G. So by this, we solve this problem. The pressure intensity at a point in a lead fluid is given as 3.924 Newton per centimeter square. Find the corresponding height of fluid when the fluid is water or oil. Oil of specific gravity 0.9. So pressure intensity P can be given is equals to 3.924 Newton per centimeter square. It is nothing but 3.924 into 10 to the power 4 Newton per meter square. Thus corresponding height Z of the fluid is given by Z is equals to P divided by rho G. For water, rho is equals to 1000. Therefore, Z is equals to P divided by rho G, 4 meter of water. For oil, 0.9 is the specific gravity. So density is equals to 900 kg per meter cube. So Z is equals to 4.41 meter of oil. On the same basis, this problem of ram has been solved, where the pressure has a ram of 30 centimeter diameter and plunger is of 0.4 centimeter diameter. That is, its cross-sectional diameter has been given. Find the weight of lifted by the hydraulic press when the force applied on the plunger is 500 Newton. So here 500 Newton pressure is applied. Calculate first the area of both, and we know that force upon area is nothing but pressure intensity due to plunger. And according to Pascal's law, pressure applied at both sides is same. So here calculate the pressure. Pressure is equals to force upon area. So force is 500 divided by area. We will get pressure. Same amount of pressure will be applied at here. Same amount of pressure will be applied at here. Now, this is last problem which we are going to see is the multi-fluid manometer. The principle which is result of Pascal's law allows us to jump from one fluid column to the next in manometer without worrying about pressure change, as long as we don't jump over a different fluid and the fluid at rest. Then the pressure at any point can be determined by starting with a point of known pressure and adding or subtracting rho GH terms as we advance toward the point of intersect. So we can say P atmospheric plus rho 1 GH1 plus rho 2 GH2 plus rho 3 GH3 is equals to P1. The open tank contains water up to a depth of 2 meter and above it an oil of specific gravity 0.9 for a depth of 1 meter. Find the pressure intensity at interface of the 2 point levels at the bottom of the tank. So at interface of 2 point level, the height is 1 meter and at water level height is 2 meters. Specific gravity of oil is 0.9, so density of oil is 900 kg per meter cube. For water it is 1000 kg per meter cube. We don't know that. So pressure intensity at any point is given as P is equals to rho into G into H. So at point A it is rho into G into H1 is equals to 900 into 9.81 into 0.1 is equals to 829 meter per meter square. For point B, P can be given as rho 2 GH2 plus rho GH1. Now we know that rho 2 is nothing but density of oil and rho 1 is nothing but density of water. So putting these values we will get P is equals to 28,449 meter per meter square. Okay. So by this we end this chapter number 1 at here. From next lecture onwards, we are going to start the chapter number 2. I hope you better understand this chapter. Actually, chapter number 1 consists all basic properties of the fluid and how to measure the fluid pressure. That part we have studied at here. So hopefully we will meet in the next chapter. Thank you very much.